Hi, I'm Mike Stanzik, and this is Digital Electronics Classroom. Thank you for joining us. Today we're going to talk about signed and unsigned numbers in binary. So it's a little bit of a longer lecture today, and I'll try to move through it as quickly as I can and get the main points here. This is, the purpose of these videos isn't to go into the super deep nitty-gritty, but to give you enough information to understand what you're doing and the procedures that you need to do binary math and manipulation. Okay, so let's get started. So this is going to be looking at unsigned and signed numbers in binary. So first thing that we're going to constrain ourselves to is that they will be fixed length. In our examples, we're going to do 8-bit. And that's important because we have to know how the sign is going to be attached to one of the bits, and we have to know how long the number is if we know which bit we're talking about. So that's an important piece we're going to need. All right, so let's start out with unsigned. Unsigned just says what it means. It's simply the magnitude of the number. There is no information about the sign. So if we have 8 bits, let's take a look at our table of n and 2 to the n. So 1, 2, 3, 4, 5, 6, 7, 8 bits with their corresponding powers of 0 to 7. And so then 2 to the 0 is 1, 2, 4, 8, 16, 32, 64, and 128. Okay. So there is, if I wanted to represent the number positive 50 in decimal here, okay, how would I write that in unsigned? Well, I need the magnitude 50 and the sign. So this is the magnitude, and this here is the sign. Okay. So I need a magnitude of 50. So let's take a look at how we can get that. So I need a 32. I'll need a 16, that gives me 48, and then I'll need a 2, that gives me 50. And so this is going to have, written from bottom to top, 0011, 0010 as its decimal number. Now this whole thing is the magnitude. So it doesn't give us any information about sign. So we actually have to put this sign external to the 8-bit number. So it's an external sign. So what about negative 50? Base 10. So that would be a negative external sign and then exactly the same number right here. Okay. Unfortunately now, we're representing inside our computer our information with zeros and ones. How do you represent the plus and minus? Because that's not a 0 or 1, it's this sort of abstract sign character that we don't have a representation for at the moment inside the computer. It's just on our paper. And so that's one of the big disadvantages of using an external sign like that. The advantage is that we do get to use the whole range of numbers. And so this goes from 0 to 255, so that whole range of numbers. Now, if you're never going to use a negative number here and you know you're just looking at the magnitude, then sure, use it unsigned, and then you can have a bigger range. Okay, so that's an unsigned binary number. Let's look at the next one, signed magnitude. Oops. Magnitude. In signed magnitude, the leftmost digit is reserved for the sign. and it is a 0 for positive and a 1 for negative. All right, so let's go ahead and make our table again here. We got n, 2 to the n. So this time, we only have 7 digits that we can use, and the 8th one is reserved for the sign. So we have 1, 2, 4, 8, 16, 32, and 64. So you can see that we have a smaller range, and so we can't get up to 255 with this set of digits. We can only get up to 127. So our range has been halved, if you will. And so because we're reserving one of the digits for the sign. So what does this look like for our examples? We have positive 50, right? So in this case, we have our sign and our magnitude. And these are explicitly represented in our signed magnitude configuration here. And so when I write this, I'm going to have a sign bit to start, and since this is positive, that sign bit will be 0. And then we're going to have the remaining bits that give us the magnitude, and that was again 32, 16, and 2, giving us a total of 50. So I have 0, 1, 1, 0, 0, 1, 0. And so here is our sign. And then the rest of these is our magnitude. Okay, so that's how we would represent a signed magnitude positive 50 8-bit binary number. What about negative 50? So here's a good chance for you to pause the video and say, okay, let me see if I can put negative 50 together. The only difference here is that the leading digit is a 1, representing that this is a negative number, and then the magnitude is exactly the same. So the magnitude there is the same as the one above. It's 50. So if I took this part as an unsigned number, 7-digit unsigned number, it would read 50. And then that leftmost one, or the most significant bit, if you will, is the sign. Okay. So what are the disadvantages here? Or some things we can say: it has a reduced range, but huge, 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 the sign is represented in binary. Sign is achieved with the leftmost bit. So we set the bit to set the sign. Okay. Now we'll go into our third one. In our last video, we talked about 1s and 2s complement, and so this is going to be, both of these have a representation for signed numbers, but I'm just going to talk about the 2s complement one because that's the one that's most frequently used. Now, it is the most confusing, I feel, but also probably the most used. I'd have to check on that myself, but I'm pretty sure it's the most common system that's used, so we want to make sure that we take a look at it. Okay, so let's go ahead. So this is signed 2's complement, and so the key thing here is we get negative numbers by taking the 2's complement. Actually, a better way to say this is that we transform the number between positive and negative by taking the 2's complement. This is reversible, if you will. So if I take the 2's complement of a negative number, I will get the positive number that has the same magnitude. And if I take the negative, or the 2's complement of a positive number, I will get the negative number that has the same magnitude. Now, the magnitude doesn't look the same in the binary number because this is not signed magnitude, this is 2's complement, so they're going to look different from each other. And that's okay. We'll do this in an example. So we need to talk about this idea of, or how, I guess, of rollover, how we represent these numbers in the 2's complement. This is where it becomes a little bit hairy, okay? And so we're going to say that I'm going to write these in decimal form and then some of the numbers here in binary form. So for our 8-bit number, 0000 is going to represent the number 0, and for the unsigned number, it would also represent the number 0. So if we increase that number, like go 1 to 2 and so on, what we're going to say is increasing it in this direction is going to give us the positive numbers. So we get positive 1 and positive 2. And that's just as you expect in terms of adding to the number 0, 0, 0, 0, 0, 0, 0, 0, 1, so on and so forth as we go up. If we go in the other direction is where we're going to get our negative numbers. So going down from 0, if you will increase in the negative direction what those numbers are. But this is not negative 1 in an unsigned situation. If I go down from 0, 0, 0, 0, this is a fixed number of digits. This is where we can roll over. So if I'm moving upwards here, it's 0, 0, 0, 0, the next one is 0, 0, 0, 1. But if I'm moving downwards, the next number that we get is actually 1, 1, 1, 1, 1, 1, 1, 1, right? And so it's rolled over to all ones. And so that's the thing that's a little bit kind of difficult to understand, is that this number now represents the number negative 1. And then if I go to the next one, in this case, it's going to be that. So I'm subtracting 1 each time, going this direction. I'm going down in number. But the real trick here happens between these two, and this is the rollover. Okay. And so we have this number is now 255, and then 254 in an unsigned situation. That's what that number would represent. Okay. So we're dividing this set of numbers into two sections. One is going to represent all the negative numbers, and one is going to represent all the positive numbers. So what's the largest number that we go up to? So in an unsigned sense, we're going to go up to the number 127, and that's going to represent positive 127, and it's going to look like this. 0, 1, 1, 1, 1, 1, 1, 1. Okay. So that's the largest positive number that we can represent. And one thing that you'll notice here is that all the numbers here are going to start with a leading 0. Now this is not signed magnitude, signed magnitude representation. Although if you just look at the positive numbers, it kind of looks like it is, right? So those would be the same if you were using signed magnitude representation. But we start, so all positive numbers start with 0. So we can recognize them, it's just not signed magnitude. And then we go down to 128 here, and that is going to represent negative 128. So half the numbers go 0 to 127 and negative 1 to negative 128. And this looks like this number, 1, 0, 0, 0, 0, 0, 0, 0. And so we also see here that all the negative numbers start with 1. So all negative numbers start with 1. Okay, so that's how we represent these numbers. So let's talk about how we get them by performing a 2's complement. Scroll scroll a little bit here. So I don't expect you to understand the 2's complement completely at this point. There's just a lot that you have to go through to sort of get the handle of it. I'm just trying to give you some of the basics at the moment, and I realize it might be a little bit confusing. You can look back at the 1's and 2's complement video and look forward at where we use it for subtraction. And I think by doing all those three things, this video and those two, then you'll start to get an idea of how this works. Okay. And so this will be helpful though. So we're going to start with positive 50. Okay, so positive 50 is going to look exactly like the signed magnitude version. So we're going to start with a 0, and then it's going to be, the rest of this is going to be 50. So 0, 1, 1, 0, 0, 1, 0. Okay, so that's going to be representing positive 50. And just to again, so we can see this, it's nice to have this in front of us. 0, 1, 2, 3, 4, 5, 6, 7. And then this is 1, 2, 4, 8, 16, 32, 64, 128. Okay, so that number there, we need the 32, the 16, and the 2, and that gives us positive 50. So how do I get to negative 50? So here's the big reveal. So you get to negative 50 by taking the 2's complement of positive 50. So I have to take the 2's complement. This is why it's a signed complement form. Okay, take 2's complement of positive 50 to get negative 50. So let's do that. So if you remember the steps, we flip for the 1's complement. So we got 1, 1, 0, 0, 1, 1, 0, 1, and then we add 1. And so we add 1. So this is going to be 1 and 1 here is a 0, carry the 1. So we got 1, 1, 1, 0, 0, 1, 1. So notice that we have a 1 in front, signifying that's a negative number, but it's not signed magnitude, and we can tell because this set of numbers here does not match this set of numbers up there. They're different from each other. So this is the difference in representation that we get between signed magnitude and 2's complement representation. So this does have a 0 in front, signifying that it is a positive number. It's positive 50. This is negative 50. So wait, how is that negative 50? If I use this in the traditional sense and say that was negative, we'd have this is 64 plus 16 plus 8 plus 4. That definitely doesn't make 50. Well, it's because it's 2's complement. We can't read it in that way. We take the 2's complement to figure out what number it is. So if I gave you this negative number and I said, well, what number is that? What you would do, as we said, 2's complement is reversible, you would take 2's complement on that number to find out what the positive number is and thus the magnitude. And so let's do that. So we take 2's again, to get back to 50. So let's do that. We'll flip. So we got 0, 0, 1, 1, 0, 0, 0, 1, and then we add 1, giving us 0, 0, 1, 1, 0, 0, 1, 0. And then notice that this is equal to our original. And so now I can use this and calculate this as 32 plus 16 plus 2, that's 50. And so 50, when we do the 2's complement, we get negative 50. We do the 2's complement again, and we get back to 50. So this is reversible. So the 2's complement is reversible. Okay. So that is the 2's complement. That's how we get it. Thanks a lot for watching. I hope you found value in that, and we'll pick up next time with some subtraction. All right, have a great day.